which is not what I was trying to do in this case. So I think what I was trying to do in this case is what I was trying to derive is the case when even before the string is loaded, even before the string is loaded, I want to have a tension on the string. Okay, so I want to, even before the string was loaded, I want the string to have a tension of strength of T. All right, so that when the string starts to get deformed, the total elastic energy would increase by T times the amount of lengthening. So basically, the elastic energy would be equal to from 0 to 1. Okay, the tension on the string times how much it has lengthened, which is going to be du dx squared times dx. All right. Sorry for the confusion. Is there any questions on what the derivation is like, or should I explain again? Okay, so let's move on from here.
I think Megan is asking some questions in the chat.
Where do I see the chat? Oh yeah, okay. Does it matter if the string has tension? Yes, actually, it matters when the string has tension, because if the string doesn't have tension in the beginning, then the elastic energy would be proportional to the square of the lengthening, and the lengthening is proportional to du dx squared. So the elastic energy would be du dx to the fourth power. Okay, so if that's the case when the string does not have any tension to start with. Okay, so we still would have the same energy minimization problem, but the problem would have a du dx to the fourth power in it, and it'll be a slightly more difficult finite element problem to solve. If the string have tension in the to start with, especially if it has a tension of T, then under small deformation, the du dx squared term would overwhelm the high order terms, such as du dx fourth order term, so that we have an easier problem to start with. All right. If you are interested, we can go over the no tension case later on. But like for the simplest equation I want to derive over here, we want to discuss the case with the tension. Is it clear? Right. So basically, if you think of the elastic energy of something of a small segment of string, right? If I don't have any tension, the energy would go like that. So it's a quadratic, and if I have a very small lengthening, the amount of elastic energy I gain is proportional to the delta x squared, in delta lengthening squared. If I already have some tension, my starting point is over here. So if I lengthen the string by a little bit, the increasing elastic energy is proportional to the amount of lengthening, right? So it's there is O delta L term. So in this case, I have O delta L squared, right? That's the difference. All right. So now I have G and E, and I need to figure out how can I minimize over all possible functions Ux, the summation of G plus E. Okay, and let me just write it a little bit more. Just plug in both integrals. What I have is g, the gravitational constant, times rho of x, which is known. And I'm going to highlight my unknown, which is u of x. Okay, and then plus t, which is also known, and this du dx squared, which is unknown, dx.